Now let us consider another arithmetic function or number theoretic function which is known as the Euler-Tauschen function. Euler-Tauschen, T-O-T-I-E-N, Euler-Tauschen function. Euler-Tauschen function is usually denoted by phi of, where n is any positive integer. Why? Because it's an arithmetic function. That's a function defined on positive integers. So, for n greater than or equals 1, the phi of n is defined as the number of positive integers not exceeding n and are relatively prime to n. Not exceeding n, there are three conditions. First is the number of positive integers not exceeding n and relatively prime to n. These are the three conditions. So that is phi of n. For n greater than or equals 1, the Euler-Tauschen function phi of n is defined as the number of positive integers less than n and relatively prime to n. Means, so what is phi of 1? Simply phi of 1 equals 1. Okay. What is phi of 2? Phi of 2 means the number of integers less than 2, not exceeding 2, and relatively prime to 2. So, how many numbers are there? That is only 1. What is phi of 3? 3. The numbers, the positive integers which are less than 3. So, 1 and 2 are less than 3. And 1 and 2 are also relatively prime to 3. Why? Because 1 and 3, GCD of 1 and 3 is 1 as well as 2 and 3 is 1. So there are how much such positive integers? There are 2 such positive integers. So phi of 3 equals 2. So what is phi of 4? Phi of 4 means counting the number of positive integers less than 4 are relatively prime to 4. 1 and 4, they are relatively prime. 2 and 4, they are not relatively prime. But 3 and 4 are relatively prime. How many positive integers which are less than 4 are relatively prime to 4? There are 2 positive integers which are 1 and 3. So phi of 3 is 2. Again phi of 4 is 2. What is phi of 7? Phi of 7 is 6. Why? Because 1, 2, 3, 4, 5 and 6, these are less than 7 and relatively prime to 7. So when P is a prime, so what is phi of P? Phi of P is P minus 1. 13 is a prime number. So what is phi of 13? All the integers less than 13, positive integers less than 13 and relatively prime to 13 are 1, 2, 3 etc. to 12. So phi of P is P minus 1. Okay, what is phi of 10? Phi of 10. 10 is not a prime. So the number of positive integers less than 10 and relatively prime to 10. 1 and 10 are relatively prime. 2 and 10, no. 2 is a common factor. 3 and 10 are relatively prime. 4 and 10, no. 2 is a common factor. 5 and 10, no. 5 is a common factor. 6 and 10, 2 is a common factor. 7 and 10, relatively prime. 8, no. 9 and 10, relatively prime. So how many integers are less than 10 and relatively prime to 10? There are 1, 3, 7 and 4 means phi of 10 equals 4. So this is a Euler-Tauschen function. Okay. So the number of positive n greater than or equals 1, then the Euler-Tauschen function phi of n is defined as the number of positive integers less than n and are relatively prime to n. Agree? Now there is an interesting result. Come to the theorem. If n greater than or equals 1, then sigma d divides n phi of n. Sigma d divides n mu of d is greatest integer 1 by n. Here sigma d divides n phi of d, not phi of n, phi of d. Sigma d divides n phi of d equals n. If n greater than or equals 1, then sigma d divides n phi of d equals n. how to prove this one? So for proving, define a set S. Let S equals set of all 1, 2, 3, 4, etc. up to U. These are the first n positive integers. Let S equals 1, 2, 3, etc. up to U. Now, you can divide this S into some disjoint sets. For that, you can define A of D. A of D is defined as, it is a set of all k such that k and GCD of k and n is D, where k ranges from 1 to n. We can define A of D equals set of all k with the GCD of k and n is D, and k ranges from where to where? K ranges from 1 to n. So, suppose so means then the A of D's are disjoint and union of A of D. Union of A of D with respect to D is always yes. Union of A of D with respect to D is always yes. Also, this A of D are means intersection with respect to D, A of D is always empty. This A of D are mutually disjoint. Why? Because we take an example. Consider, suppose S equals set 1, 2, 3, 4, etc. to 10. So what is A of 1? 1 is a divisor of 10. Okay. What is D divides 10? 1 is a divisor of, S. So A of 1, you can find out number of k's such that here n greater than or equals 1. Suppose n equals 10. N equals 10. So, number of k's with the k and GCD of k and n is D means here it is 1. The numbers which are relatively prime to 10 are 1 and 10 are relatively prime. 3 and 10 are relatively prime. Then 4, 5, 6, 7 and 10 are relatively prime. 9 and 10 are relatively prime. A of 1 equals 9. When n equals 10. What is suppose 2 is the divisor of 10. What is A of 2? A of 2 means GCD of k and 10 are 2. Which are them? So 2 and 10 are 10 has GCD 2, 4 and 10 GCD 2, 6 and 10 GCD 2, 8 and 10 GCD 2. Okay. 3 is not a divisor of 10, 4 is not a divisor of 10, 5 is a divisor of 10. You have 5, D is a divisor of 10, n equals 10. So you have 5, what is GCD of k and 10 equals 5, which is 5 and 10. Now only 10. 10 is a divisor, so there is only such a 10. So listen, A1, A2, they are mutually disjoint. A2, A5, mutually disjoint. All of these AAs, ADAs are mutually disjoint. But what about the union? A1 union, A2 union, A5 union, A10 is nothing but this yes. So, like this. You can find out such a, or you can divide this S into such a mutually disjoint sets whose union is nothing but A of D. Clear? Okay. Now, let F of D denotes the number of integers in A of D. Let F of D denotes the number of integers in A of D. Means, number of integers in A of 1. What is F of 1? F of 1 is 4 here. Okay. What is F of 2? F of 2 is again 4. Yes. What is F of 5? F of 5 equals 2. And what is F of 10? F of 10 equals 1. Yes. So let n be let F of D denotes the number of divisors, the number of integers in A of D. Okay. So, what about sigma d divides n f of d. Sigma d divides n f of d equals n. Clear? Okay. So here, yes, here a10 is not a10 is not required. Sorry. Why? Because it is as less than 10. So here f of 1 equals 4, f of 2 equals 4, f of 5 equals 2, where f of t denotes the number of integers in a of t. Clearly, what is sigma d divides n f of d? Sigma d divides n f of d equals 1. Why? Because sigma d divides n f of d means f of 1 plus f of 2 plus f of 5, that is 10 here. How many integers in S? So 10. So sigma d divides n f of d is number of integers in S. Okay. Where f of d be the number of integers in a of d. Now, but we can choose this k in such a way that this k and n are GCD of k and n is d. GCD of k and n is d means this k by d and n by d are relatively primes. Okay. Moreover, k ranges from where to where? K ranges from 1 to n. K ranges from 1 to n means it is 1 less than or equals k by d less than or equals n by d. Okay, so it is 0 less than. As it is k by d, when k less than or equals n, then k by d less than or equals n by d. Sure. Okay. Now let it be q. Suppose q less than or equals n by d. Let k by d is q, so q less than or equals n by d. Then from here we can clearly see that there exists a 1-1 correspondence between the elements in a of d and those integers satisfies 0 less than q less than or equals 0 less than q less than or equals n by d. There exists a 1-1 correspondence in a of d. Suppose d is 1, 3, 7 and 9. Okay. Which are the integers in this S which satisfies this condition? When d equals 1, 0 less than q less than or equals n by d. What is q? Q is k by d. Okay. So it is 1, 3, 7 and 9. There is again, so there is a 1-1 correspondence in A1 and the integers which satisfies that. So generally we can say that there exists a 1-1 correspondence between the elements in A of d and those integers which is satisfying 0 less than q less than or equals n by d with this q and n by d are relatively primes. Why? Because A of 1 is 1, 3, 7, 9 and 0 less than or equals q less than or equals n by d with the q and n by d are relatively prime is also these numbers. Okay, there is no such other numbers. So there exists a 1-to-1 correspondence between the elements in A of d and the numbers which satisfies 0 less than q less than or equals n by d with the q and n by d are relatively primes. Okay. So listen. So what about the such numbers? The number of such q's is phi of n by d. Why? Because of the definition of this Euler-Torsion function. How we define it? Euler-Torsion function phi of n is nothing but the number of positive integers less than n and relatively prime. So here the number of such q's is always phi of n by d because the numbers which is less than n by d and relatively prime to n by d. Number of such elements less than n by d and relatively prime to n by d. So it is phi of n by d. Okay. Right. So means what is f of d? We define this f of d is number of what is f of d? F of d be the number of elements in A of d. But here the number of such elements is phi of n by d. Therefore we can say that this f of d equals phi of n by d. Okay, they are same. F of d equals phi of n by d. So what is sigma d divides n f of d? Sigma d divides n f of d equals sigma d divides n phi of n by d. Clear? Sigma d divides n phi of n by d. But what is sigma d divides n f of d? That is n. So that implies sigma d divides n phi of n by d equals sigma d divides n f of d but sigma d divides n f of d equals n. So sigma d divides n, phi of n by d equals n. Okay. But d runs through all divisors of n. Also, it runs through all divisors of n by d. D runs through all divisors of n. Okay, d be the divisor of n. So this d runs through all divisors of n by d also. Sure. Okay. So this phi of d is equivalent. Phi of d is equivalent to phi of n by d. Phi of d is equivalent to phi of n by d. So therefore, this implies sigma d divides n. So instead of phi of n by d, it is phi of d. So sigma d divides n. Sigma over d divides n phi of d equals n. Okay. So this is our important result.